There will be a scientific theory of deep learning. Jeremy Cohen Flatiron Institute. Arthur Jackett New York University. Nikhil Ghosh Flatiron Institute. Mason Kam Stanford University. Dhruva Karkata UC Berkeley. In this paper, we make the case that a scientific theory of deep learning is emerging. By this we mean a theory which characterizes important properties and statistics of the training process, hidden representations, final weights, and performance of neural networks. We pull together major strands of ongoing research in deep learning theory and identify 5 growing bodies of work that point toward such a theory. Solvable idealized settings that provide intuition for learning dynamics in realistic systems. Tractable limits that reveal insights into fundamental learning phenomena. Simple mathematical laws that capture important macroscopic observables. Theories of hyperparameters that disentangle them from the rest of the training process, leaving simpler systems behind, and universal behaviors shared across systems and settings which clarify which phenomena call for explanation. Taken together, these bodies of work share certain broad traits. They are concerned with the dynamics of the training process. They primarily seek to describe coarse aggregate statistics, and they emphasize falsifiable quantitative predictions. We argue that the emerging theory is best thought of as a mechanics of the learning process and suggest the name learning mechanics. We assert that learning mechanics should be a mathematical theory, grounded in first principles calculations that closely predict empirics, reliant on well-tested approximations and assumptions, aiming for broad impact across the machine learning stack once it reaches maturity. We discuss the relationship between this mechanics perspective and other approaches for building a theory of deep learning, including the statistical and information theoretic perspectives. In particular, we anticipate a symbiotic and mutually supportive relationship between learning mechanics and the developing discipline of mechanistic interpretability. Where mechanistic interpretability aims to be the biology of deep learning, learning mechanics should aspire to be its physics, mirroring the complementary relationship between biology and physics in the natural sciences. We also review and address common arguments that fundamental theory will not be possible or is not important. We conclude with a portrait of important open directions in learning mechanics and advice for beginners. We host further introductory materials, perspectives, and open questions at learningmechanics.pub. 1. Introduction. Deep learning is famously a black box learning method, the most powerful, most inscrutable, and now most technologically important member of the machine learning pantheon. Properly trained, neural networks learn to perform a wide array of tasks with superhuman performance, but we have no unified scientific framework that explains why or how. Motivated by both scientific curiosity and the promise of practical engineering benefit, the effort to put rigorous mathematical and scientific backing behind this applied discipline has spanned decades. Despite some progress, however, our understanding remains primitive. Neural networks are still trained using methods discovered largely through trial and error rather than first principles, and theory plays little role in the day-to-day practice of deep learning. The challenge has only compounded as practice has advanced, and in the era of large language models and diffusion models, the mysteries are arguably deeper than they were 1 or 2 decades ago. Will we ever understand? This paper makes the case that, yes, there will be a scientific theory of deep learning, that we can see pieces of this theory starting to emerge, and that this theory will take the form of a mechanics of the learning process. The questions driving deep learning theory have changed over time, and to understand where the field is going, it is useful to first look back at how we got here. Deep learning theory is as old as machine learning itself, with roots in the McCulloch-Pitts neuron and the perceptron in the middle of the last century. The earliest theoretical questions in machine learning were about expressivity. What functions can simple models represent, and how can they be learned from data? As learning came to be understood as a statistical problem and simple learning systems found practical success, the theoretical focus shifted to ask, when does learning from finite samples generalize? This gave rise to classical learning theory, including statistical and computational/pack learning theory. Paired with classical optimization theory, These frameworks gave clean end-to-end guarantees of the optimization and generalization of simple learning systems. In parallel, a classical tradition of the statistical physics of machine learning developed satisfying theories of the average case behavior of simple models. While these classical theories built a strong foundation for understanding learning, the rise of deep learning through multi-layer networks, backpropagation, and increasing scale in both data and compute exposed limitations in their explanatory power. Neural networks are complex, non-convex, and over-parameterized, in contrast with the simple, convex, parsimonious models for which classical learning theory excels, and they optimize and generalize better than these classical approaches can guarantee or explain. Furthermore, it became clear that neural networks were not merely fitting data or achieving low training error, they were learning structured internal representations and displaying striking regularities across tasks and scales. The classical questions of performance and efficiency remained important, but answering them would first require understanding a new host of phenomena shaped both by the dynamics of neural networks through training and the structure of the data they are trained on. This marked a transition in which deep learning theory changed in character from a largely mathematical study of what is possible to a truly scientific effort to describe, explain, and ultimately predict the behavior of complex empirical systems. New scientific endeavors often start with an empirical tension in which nature presents something interesting we cannot predict or explain with existing tools, and although neural networks are artificial computational systems, this same scientific tension is present here. We should thus approach this task as scientists, embracing empirics, seeking unifying principles, and identifying recurring motifs. We should also expect the path forward to look more like the development of a scientific field than the development of a mathematical one. The purpose of this paper is to convince the reader that this scientific tension is gradually giving way to a scientific theory which resolves it. In Section 2, we pull together major strands of ongoing research and identify 5 lines of evidence that such a theory is emerging. There are a growing number of analytically solvable settings in which learning is fully captured by simple mathematics, including but not limited to deep linear networks and kernel methods, Section 2.1. There exist useful limits, including limits of infinite width and depth, that provide insight into fundamental learning behaviors, Section 2.2. In many cases, simple empirical laws suffice to capture meaningful macroscopic statistics, including test time performance and loss landscape sharpness, Section 2.3. Many of the hyperparameters governing optimization can be disentangled and understood, leaving behind a simpler effective dynamical system, Section 2.4, and as applied deep learning has scaled up and converged on best practices, universal phenomena have increasingly appeared across settings and tasks, Section 2.5. These lines of research broadly share several overarching characteristics. They are concerned with the dynamics of the training process. They primarily seek to describe coarse aggregate statistics of learning, and they emphasize accurate average case predictions over rigorous worst-case bounds. In this sense, the emerging scientific theory of neural networks appears to have much in common with theories in physics, such as classical mechanics, continuum mechanics, statistical mechanics, and quantum mechanics. We argue that this emerging theory is best understood as a mechanics of learning. 1.1 What's in a mechanics? Mechanics is the branch of physics studying how forces acting on objects determine their movement through space and time. Neural network learning can be thought of in this way. Much as an object moves continuously through physical space, learning involves a model moving through parameter space via discrete updates. In the physical sciences, forces come from interactions between components of a system. Similarly, the process of deep learning is shaped by interactions between the parameters, dataset, task, and learning rule. In physics, these forces are mediated by fields. In deep learning, they are mediated by gradients. In physics, systems settle into equilibria at local minima of a potential determined by internal interactions and external constraints. Analogously, neural networks converge to local minima of a loss landscape shaped by their architecture and training data. While the systems under study are very different, since the key problems of both are essentially about movement and interaction, we might expect some features of the resulting sciences to be shared. These analogies are not just speculation. We can see these similarities reflected in the lines of research listed above. All branches of mechanics, and especially classical mechanics, develop a library of analytically solvable settings to gain intuition. So too does learning mechanics. All branches of mechanics use limits as simplifying tools. So too does learning mechanics. Continuum and statistical mechanics, the branches which most directly deal with large numbers of interacting components, describe zoomed-out summary statistics rather than the motion of every particle. This has also proven a useful approach in dealing with the complexity of deep learning. Every physical system has one or more system parameters, characteristic scales, coupling constants, etc., affecting its behavior, and some techniques for treating these are essentially the same as those used to study hyperparameters in deep learning. Finally, physics is full of cases in which the same phenomena show up in very different settings, and similarly, we see universal behavior emerging across deep learning systems. All considered, the emerging science shares deep similarities with established branches of mechanics. By analogy to classical, continuum, statistical, and quantum mechanics, we suggest the intended theory be called learning mechanics. 7 desiderata for learning mechanics. We should be clear at the outset what we want from a mechanics of learning. Assessing how mature branches of mechanics were motivated, developed, and succeeded, we can see what sort of goals to aim for. Here are 7 desiderata for this research program. Learning mechanics should be fundamental, proceeding logically from a first principles description of neural network training. Interim assumptions about network weights, dynamics, and performance will be useful tools, but they should ultimately be explained from first principles. Learning mechanics should be mathematical, making unambiguous quantitative statements about important properties of neural networks. No mechanics is a qualitative science, neither will be learning mechanics. Learning mechanics should be predictive, making claims supported by simple, repeatable empirical measurements. We have excellent experimental control of our system, and every major development should be unambiguously verified in experiment. Learning mechanics should be comprehensive, describing aspects of neural networks' training process, hidden representations, and final weights in a single picture. It is worth emphasizing that this theory will not, and should not, aim to describe everything. A map at the full resolution of the world would be the size of the world and thus of little use. What we seek instead is a theory that operates at the right level of resolution, one that sacrifices detail in favor of insight. Learning mechanics should be intuitive, being simple, illuminating, and satisfying in its demystification of deep learning. Like physics, learning mechanics should strive for simple insight over technical complexity. Learning mechanics should be useful, serving as the scientific foundation for applied deep learning as physics does for other forms of engineering. Concrete goals should include greatly reducing the need for hyperparameter tuning, giving predictive tools for dataset design, and providing rigorous foundations for AI safety work. Finally, learning mechanics should be humble, being solid in what it describes and explicit about what it cannot. Every branch of physical science has a regime of applicability outside of which it breaks down, and these boundaries are taught together with the science so that it may be used reliably. We anticipate the mechanics of learning applicable to realistic deep learning will break down in many small-scale, handcrafted, or otherwise special cases, and this is the price we will pay for the right simple picture in the regimes we care about. A mechanics of learning with these virtues, one that is fundamental, mathematical, predictive, comprehensive, intuitive, useful, and humble, would be transformative, paradigm-setting. We expect such a theory would resolve important open questions that have long remained out of reach, as we discuss in Section 5. 1.2 Why learning mechanics matters. Building learning mechanics will not be easy. It will require sustained effort, both intellectual and institutional. It is therefore worth being clear about why such a project matters. The reasons to seek a mechanics of learning fall into 3 broad categories: scientific, practical, and safety-related. The scientific reasons concern what such a theory could teach us about intelligence and the natural world. The striking engineering success of large neural networks suggests that they exploit deep principles of learning and representation that we do not yet understand. This has historical precedent. Technology has often preceded scientific theory, as was the case with steam engine's role in motivating thermodynamics, which went on to explain much more than engine efficiency. A similar story played out in flight. The development of airplanes through trial and error and inspiration from the natural world helped motivate aerodynamic theory, which in turn enabled both better aircraft design and a deeper understanding of how birds themselves fly. In our case, the principles that govern learning in artificial neural networks may also shed light on our own biological intelligence, with potentially important implications for neuroscience and cognitive science. The practical reasons concern the design and development of real-world AI systems. A mature theory of deep learning could guide model design, optimization, scaling, and deployment, replacing trial and error with more reliable principles. Theory has already begun to play this role in a limited but growing number of cases, including empirical scaling laws, Section 2.3, mathematical prescriptions for hyperparameter scaling, Section 2.4, and theoretically motivated optimizers and methods for data attribution, Section 4. A deeper, more complete theory will give more such guidance and make it sharper and more predictive. The safety reasons concern our ability to describe, characterize, and govern increasingly powerful AI systems. Some form of regulation will likely be necessary, but it is difficult to regulate a technology that we cannot clearly describe. A theory that identifies the relevant variables, mechanisms, and organizing principles of large models could help provide the clarity needed for reliability, oversight, and control. One avenue by which fundamental theory might aid in AI safety is by supporting mechanistic interpretability, a point to which we return in Section 3. 1.3 Plan for this paper. This paper is structured as follows. In Section 2, we present our 5 lines of evidence that a scientific theory of deep learning is beginning to emerge. We motivate each line of evidence with an intuitive explanation and highlight examples of research successes that illustrate the underlying principle. In Section 3, we discuss the relationship between learning mechanics and other perspectives on the science of deep learning, including a possible symbiotic relationship between learning mechanics and mechanistic interpretability. In Section 4, we review and address common arguments that fundamental theory will not be possible. In Section 5, we give a portrait of 10 important open directions in learning mechanics, from predicting scaling laws to eliminating hyperparameters, where we expect to see major progress in the coming years. Finally, in Section 6, we offer some advice for young researchers looking to get involved in this scientific project and extend a hand with some introductory resources. We write this paper for a broad audience. We hope the veteran scientist of deep learning will find something valuable in our synthesis of useful approaches and results, and feel galvanized by our depiction of an emerging science. We hope to convince the deep learning practitioner that theory is on a path to fulfilling its long-standing promise of practical utility, and to encourage them to experiment with their systems with an eye for science. We hope to convince the AI safety or mechanistic interpretability researcher that white box theory is difficult yet possible, that a first principles study of dynamics can help put solid foundations beneath their important work, and that our communities should work together. See Section 3 for our vision of symbiosis. Lastly, we hope to make it easier for young students and newcomers to the field to get involved. This is an exciting and important area of work, and while it requires some mathematical maturity to get started, it is our belief that the barrier to entry could be much lower. Various deep intuitions about this science have been percolating inside the theory community for a while, and this paper is an attempt to state them clearly. We hope to make it easier for folks with the requisite background to quickly get up to speed and contribute to evidence of an emerging mechanics of learning. A great cause for optimism that a mechanics of learning is possible is the fact that the essential ingredients of deep learning are both explicit and measurable. A deep learning system is characterized by the following components. Architecture. a neural network f, x, theta, specified as a composition of simple linear and nonlinear transformations. Data, a dataset D equals x subscript I, y subscript I equals 1 to the power n, consisting of samples from an unknown data-generating distribution, x, y, tilde operator p subscript data. Task, an objective L, theta, measuring the performance of the network, f, x, theta, on the dataset, D. Learning rule, a gradient-based update equation, e.g., theta to the power t plus 1 equals theta to the power t minus eta nabla L, theta to the power t, together with a parameter initialization, e.g., theta subscript I to the power 0, tilde operator n, 0, alpha subscript init to the power 2, and optimization hyperparameters, e.g. learning rate, eta. Nothing about the learning process is hidden. Unlike many complex systems where the equations governing dynamics must be inferred from observations, deep learning directly exposes its equations of motion. Moreover, these dynamics are extraordinarily measurable. Every weight, activation, gradient, and loss value can be recorded, along with arbitrary statistics derived from them. As a result, deep learning experiments are unusually easy to design, replicate, and interrogate, making it more straightforward to discover empirical regularities and rigorously test theoretical predictions. Few fast-moving scientific domains offer comparable transparency in their governing equations or comparable freedom in what can be measured. What, then, stands in the way of a scientific theory of deep learning? The central challenge is not opacity, but complexity. While we have direct access to the architecture, data, task, and learning rule, the interaction of these components gives rise to learning dynamics that are nonlinear, coupled, and high-dimensional. These dynamics depend in subtle ways on the choice of hyperparameters. And even though we can inspect every training sample, data distributions are complex and have defied simple characterization. Nevertheless, we argue that this complexity conceals underlying regularities and that deep learning will indeed admit a scientific theory. In what follows, we present 5 broad observations that serve as evidence for an emerging mechanics of learning. Each of these admits direct analogies to tools and ideas in other disciplines of mechanics. These are summarized in Table 1. Table 1. Useful tools and ideas in the emerging science of deep learning closely resemble important tools and ideas from physics, particularly classical mechanics, continuum mechanics, statistical mechanics, and quantum mechanics. Extrapolating, this suggests that there will be a mechanics of learning which offers a unifying first principles theory of the training process, hidden representations, final weights, and test time performance of neural networks. 2.1 Analytically solvable settings exist. A reliable way to build scientific understanding in complex systems is to study pared-down yet representative settings in which quantitative calculations are possible. For example, physics uses representative solvable settings like the harmonic oscillator and the hydrogen atom as sources of intuition for much broader classes of system. Deep learning appears to be particularly amenable to this approach. Scientists have identified a rich landscape of minimal models where the learning dynamics simplify and many quantities of interest become solvable. These analytically tractable cornerstones are useful because they reveal phenomena and mechanisms to look for when we turn to realistic deep learning, to the power 1. One particularly fruitful simplification is linearization. Here we discuss 2 distinct instantiations of this idea: linearization in the data, where f, x, theta becomes linear in x, and linearization in the parameters, where f, x, theta becomes linear in theta. Linearization in the data. A deep linear network is obtained by removing all nonlinearities from a neural network's architecture, yielding a model that is linear in its inputs, x, but remains highly nonlinear in its parameters, theta. A function f of x and theta is a product of matrices W from L down to 1 times x. Deep linear networks have a long history of study because, despite their simplicity, they retain many hallmark behaviors of deep learning. These include saddle point-dominated loss landscapes, dynamics with sharp phase transitions and separation of timescales, edge of stability oscillations with gradient descent, and strong initialization-dependent inductive biases. Analysis of these networks is typically carried out with the gradient flow learning rule, the continuous time limit of gradient descent, under simplifying assumptions on. Figure 1. Linearization yields exact solutions that match experiments. A canonical work by Sachs et al. Showed that, under a task-aligned initialization, theta to the power 0 and whitened inputs x tilde operator n 0 I. The gradient flow learning dynamics of deep linear networks decouple into independent solvable Bernoulli ODEs. This leads to sequential learning of singular modes, with larger singular value modes emerging first. Panel A reproduces Figure 3 of Sachs et al. B. Linearizing a nonlinear network by truncating nonlinear terms in its Taylor expansion around initialization reduces least squares training to kernel ridge regression with the neural tangent kernel, NK. This analysis connects the network's architecture to its inductive bias through the NTK eigenstructure, enabling accurate predictions for the test performance of these networks. Panel B is based on Figure 2 of Simon et al. The data distribution and with carefully chosen initializations Fukumizu, Sachs et al., Tarmoun et al., Domini et al. In these regimes, the learning dynamics can often be solved exactly or reduced to low-dimensional dynamical systems. Across many such analyses, a consistent lesson emerges. Learning exhibits a greedy low-rank bias, acquiring some components of the task before others. Canonical work by Sachs et al. First showed how deep linear networks learn singular vectors of the input-output correlation sequentially during training, with learning prioritized toward modes associated with the largest singular values. As shown in Figure 1, this bias has been hypothesized to benefit generalization by separating the signal from the noise, and closely mirrors behavior observed in nonlinear networks, where simpler functions are often learned before more complex ones. Moreover, a range of factors, including small initializations, increased depth, stronger mini-batch noise, and explicit subscript 2 regularization, Zien et al., Wang and Jacket, have all been shown to further strengthen this greedy learning bias. Linearization in the parameters. A linearized network is obtained by truncating the nonlinear terms in a network's Taylor expansion around its initial parameters. This yields a model that is linear in its parameters, theta, but remains highly nonlinear in the data, x. The linear approximation of a function f at theta_0 is the function value plus the gradient dotted with the difference between. This is not some contrived construction. In fact, there are settings in which a model is well approximated throughout training by its linearization, i.e., for all t, f, x, theta subscript t is almost equal to f subscript ln x, theta subscript t. For example, any neural network architecture can be driven into the linearized regime by taking suitable limits, as discussed in Section 2.2. Additionally, recent evidence suggests that language model fine-tuning occurs in a near-linearized regime. Since a linearized network is linear in its parameters, its learning dynamics are identical to those of linear regression, with one key difference. While the dynamics of linear regression are driven by the Gram kernel, k subscript gram, x to the power equals x to the power down x to the power, linearized networks are described by the neural tangent kernel, and k subscript ntk, x to the power equals nabla subscript theta f x. Theta subscript 0 to the power down nabla subscript theta f x to the power theta subscript 0. When the task is least squares regression and training uses small step gradient descent, the dynamics are analytically tractable and the final predictor is given by kernel ridge regression with the NTK. This setting yields insight into a variety of deep learning phenomena. For example, since the details of the network architecture influence the mathematical structure of the NTK through the fixed feature map, nabla subscript theta f, theta subscript 0, one learns how the linearized model's inductive bias follows from its architecture. Aurora et al., Giefman et al. Furthermore, One may accurately predict the model's expected generalization error on arbitrary targets, f to the power star operator, by accounting for the structure of the input data, as shown in Figure 1. Applying this framework to realistic data distributions uncovers the origin of the typical model's tendency to learn simple and generalizing functions. Linearized models also capture relevant phenomena such as double descent and scaling laws. However, despite these theoretical merits, linearized networks are unrealistic in a few critical ways. Most notably, they do not capture the strong feature learning capabilities that generic neural networks exhibit, often leading to overly pessimistic predictions for sample complexity. Moreover, by reducing training to a tractable linear problem, these models sidestep the intrinsically non-convex optimization phenomena of deep learning. To describe these and other aspects of deep learning, one must look beyond linearization. Beyond linearization. An important frontier for theory lies in developing analytically tractable toy models that remain genuinely nonlinear in both the data and the parameters. See Open Direction 1. In these settings, the influence of the data distribution becomes more complex, making it difficult to obtain a unified and general framework. However, a growing body of work is progressing in this direction by isolating specific nonlinear mechanisms and making them solvable under assumptions on the data. One line of work studies Gaussian inputs and structured targets, e.g., single and multi-index models. Fully nonlinear neural networks provably outperform kernel methods using fewer samples because they exploit the structure in the target function to learn relevant features. Abe et al., Damian et al., Baetti et al., Ba et al., Dondi et al. Complementarily, methods from statistical physics enable computing exact asymptotics for Bayes optimal inference and learning dynamics in these models. A related setting is two-layer neural networks with quadratic activation functions, where recent results have characterized the exact asymptotics, training dynamics, and scaling laws. Several other lines of research isolate distinct nonlinear phenomena, the convergence of homogeneous networks trained on logistic losses to max-margin solutions, the reduction of training dynamics to low-dimensional summary statistics in teacher-student models, memorization in associative memory models. Learned algorithmic structure in modular arithmetic tasks. Nonlinear solvable models of attention, Zhang et al., Boncaralho et al., and improved scaling laws from nonlinear feature learning. Taken together, these approaches illustrate both the promise and the limitations of current nonlinear toy models. Each captures a slice of fully nonlinear learning dynamics, yet no unified framework has emerged. We view this space as an open and rapidly evolving area and return to these challenges in our discussion of open problems in Section 5. 2.2 Insightful limits reveal fundamental behavior. Modern deep learning systems are enormous. They regularly involve hundreds of interacting architectural components comprised of hundreds of billions of parameters and trained on trillions of tokens. With so many interacting degrees of freedom, constructing detailed microscopic theories that track individual parameters in practical systems seems all but hopeless. Fortunately, complex systems often simplify when approximated as effectively infinite in size, revealing simple mathematical structure that remains informative even for the original finite system. This strategy is well established in statistical and chemical physics. For example, the ideal gas law, PV equals nRT, is derived in a limit of infinite number of particles, often termed the thermodynamic limit, yet accurately describes real parcels of gas of finite volume. Limits are a central mathematical tool for managing the complexity of deep learning, and their recurring success in doing so provides strong evidence for an emerging theory. Figure 2. Large and small network output multipliers are sufficient to induce lazy and rich training dynamics. We train a shallow student network, f caret x equals alpha over n sigma I equals 1 n a subscript I real u, w subscript I to the power down x, with width n equals 200, to match a teacher network. F to the power asterisk operator, x, equals sigma I equals 1 3 a subscript I to the power asterisk operator real u, w subscript I to the power asterisk operator, to the power down x. On two-dimensional input data, we plot the training trajectories of the student weights, W subscript I, color denotes SGN, a subscript I, against the teacher feature directions. Left, with alpha equals 0.1, the dynamics are rich. The student weights grow significantly and cluster in angle around the teacher feature directions. Right, with alpha equals 30, the dynamics are lazy. The student weights move negligibly during training, even though the loss drops. Experiment reproduced from Chizat et al. Here we discuss the limit of infinite width in detail. We conclude by mentioning other limits and offering some unifying ideas. The infinite width limit and the lazy/rich dichotomy. The dynamics of a deep neural network often simplify when one takes the number of neurons in each hidden layer to infinity. Such a limit generally leads to so-called mean field behavior, in which we only need to describe the evolution of the neuron population as a whole, as e.g. a probability distribution, and we can ignore what each individual neuron is doing. However, achieving this limit requires shrinking the initialization scale as width increases to prevent activations in deeper layers from diverging. The key subtlety in taking the infinite width limit is that the rate at which we suppress these initial weights strongly influences the resulting training dynamics, leading to one of two qualitatively distinct limiting behaviors: the lazy, kernel, or linearized regime. The first forays into the land of infinite width studied only a network statistics at initialization, not its training dynamics. These works found that, in order for the inputs to hidden neurons to neither vanish nor explode as width increases, the parameter size at initialization has to decay as width to the power -1/2. This is not a surprise. It is just the well-known LeCun initialization rule, which can be easily derived from the central limit theorem. Later works that tried naively training the parameters of these infinite-width networks found the surprising fact that the network's weights and hidden representations change only negligibly. Yet these small changes accumulate to produce substantial changes in the output function. As a result, the training dynamics are linear in the parameters in the sense discussed in section 2.1, and the evolution of the target function may be expressed entirely in terms of the NTK. While a network in this limit is wonderfully analytically tractable, the fact that its hidden representations do evolve only negligibly means that it fails to exhibit feature learning. While the definition of feature learning is much debated, see Open Direction 4, all agree that at minimum it requires the network's hidden activations on a given data sample to change from their values at initialization, which does not happen in this limit. This suggests the NTK infinite width limit is not the right one to study. Networks in this linearized regime were later termed lazy by Chizat et al. The rich, active, or feature learning regime. In answer to this, several authors identified an alternative infinite width limit in which training does induce feature learning. The key insight was essentially to downscale the final layer weights by a factor of width to the power -1, rather than the earlier width to the power -1/2, thereby forcing the network weights to change more to compensate to the power 2. While this makes the function trivial at initialization, at infinite width it is uniformly 0. It can still grow non-trivially during training, changing by an order 1 amount upon each gradient step. This downscale the network output idea first appeared in the shallow, mean field networks of May et al., Rotzkopf and van den Einden, and Chizat and Bach, Geiger et al., and Yang, and who found that this idea also works for networks of arbitrary depth, bundling the resulting hyperparameter scaling factors together into the celebrated maximal update parameterization. Discussed in section 2.4, it is now widely accepted that infinite-width neural networks can learn features. Wide networks in this rich regime display a huge range of interesting behaviors that their lazy counterparts do not. The most significant is certainly that the hidden features of these networks change over time, adapting to the structure in the input data, altering the internal geometry of hidden representations over the course of training. Subpopulations of neurons specialize, learning to attend to different features latent in the data. For instance, in tasks where the optimal predictions involve low-dimensional subspaces of high-dimensional data, the distribution over first layer weights evolves to amplify weights in the subspace of interest. May et al., Abe et al., Manirai et al., Chui et al., De Filippis et al., Erba et al., Montanari and Wang. When the scale of the initialization is made even smaller, they often show the greedy low-rank bias discussed in section 2.1, acquiring some components of the task before others, to the power 3. The lazy-rich dichotomy, and its dependence on initialization scale, emerged as a central finding of infinite-width analyses. Subsequent work has shown that analogous behavior appears even at finite width. Scaling down the network output promotes feature learning, pushing models toward the rich regime, whereas increasing the output scale tends to linearize training dynamics and induce lazy behavior. This sensitivity to initialization scale connects to a broader literature on inductive bias, where seemingly small changes to the learning setup can steer training toward fundamentally different solution classes. Figure 2 illustrates how the same finite network, trained with different output scalings, can exhibit either lazy or rich learning dynamics. The infinite depth limit and other hyperparameter limits. As with infinite width, one can arrive at a stable infinite depth limit of a deep residual network by downscaling the contribution of each layer so the residual stream does not blow up. Here, too, there are different limiting behaviors depending on the size of this downscaling factor. Suppressing each layer by a factor of depth to the power -1 results in limiting dynamics in which the residual stream changes smoothly over depth, reminiscent of neural ODEs, while suppressing each layer by a factor of depth to the power -1/2 results in limiting dynamics in which the residual stream diffuses as if driven by a stochastic differential equation. Networks in these two limits converge to qualitatively different solutions in realistic architectures such as transformers. It is not yet clear which is the more important limit to study. Some deep learning architectures admit size limits other than those of large width or large depth. Instead of increasing size or total number of distinct feed-forward layers, one can also analyze the infinite limits of recurrent architectures using similar mean field ideas. State-of-the-art transformer models include more expressive constituent blocks such as multi-head self-attention layers and mixture of expert multi-layer perceptrons. These layers have multiple scaling directions including head count, head size, and context length for attention, Ron et al., Bordelon et al., and expert count, expert size, and sparsity for mixture of expert models. Clarifying the interplay of different infinite limits in these models is important to making contact with modern practice and to disentangle various hyperparameters related to initialization and optimization. See section 2.4. Lastly, most optimization hyperparameters have an associated limit. As the batch size approaches infinity, we reach population gradient descent. As we take learning rate to 0, we recover gradient flow. If we add an infinitesimal weight decay and take training time to infinity, we first optimize the loss to convergence, then perform parameter norm minimization conditioned on the final value of the loss. We discuss how to understand the corrections induced by having finite values for some of these hyperparameters in section 2.4. Joint scaling limits. Sometimes scaling limits in multiple variables, nu subscript 1, nu subscript 2, play nicely, in the sense that lim nu subscript 1 infinity lim nu subscript 2 infinity gives the same result as lim nu subscript 2 infinity lim nu subscript 1 infinity. For example, the infinite width and depth limits in residual networks usually commute in this way, so long as one takes a sensible parameterization. However, in many theoretical machine learning settings, different scaling dimensions do not commute, and the limiting behavior could depend on a limiting ratio, nu subscript 2/nu subscript 1. Such joint/proportional scaling limits are common in random matrix theory. For example, consider the SVD of a random matrix with p rows and n columns with n, p infinity, with p/n held constant. In machine learning theory, neural networks trained with random data can often be described by a joint scaling limit where both the dataset size and parameter count are taken to infinity, but one or more of the ratios. Data over input dim, data over width or data over parameters is a finite value, Sung et al. Saad and Salas, Dibarova and Krisakala. Lee and Sompolinsky-Maillard et al. Martin et al. Barbier et al. This joint scaling is likely necessary in the study of compute-optimal neural scaling laws where the training horizon, i.e. dataset size, is scaled linearly with the total parameters and to theoretically characterize hyperparameter transfer phenomena Bordelon and Padovan. These joint, data, and model size limits are potentially important as infinite parameter limits at fixed dataset size are capable of perfect interpolation and do not capture scaling law behaviors across model sizes. See Section 2.3. Other well-studied joint scaling quantities include the ratio, width over depth, in non-residual networks, the ratio, learning rate, in the rich regime, and the SGD noise temperature, learning rate. The discretization hypothesis. Overall, the widespread use of limits to manage the complexity of deep learning reflects a recurring theme across scientific disciplines. Appropriate asymptotic perspectives often render otherwise intractable systems analytically tractable. Many theorists share a heuristic belief that most practical neural networks can be understood as noisy, finite approximations to models of infinite size to the power 4, by analogy. One numerically solves a partial differential equation by discretizing over space and time, and the finer the discretization, the smaller the numerical error from the desired continuum process. This is very possibly also true of deep neural networks, with width and depth taking the place of space and time. Other finite hyperparameters, such as the learning rate, batch size, and dataset size, might also be understood in this way. We might call this belief the discretization hypothesis. While it has yet to be made precise or proven, see Open Direction 5, this hypothesis has implicitly underpinned much important work, and little in the analytical study of large models makes sense without it. The discretization hypothesis amounts to the statement that finite-size corrections from limits typically worsen performance, while saving costs in data, time, memory, and compute, showing that these finite-size effects deliver a general benefit that cannot be achieved any other way would falsify this hypothesis. 2.3 Simple empirical laws capture meaningful macroscopic statistics. Deep learning is highly measurable. It is easy to track a vast array of quantities before, during, and after training. While any quantity can be measured, the most lawful are typically aggregate, macroscopic statistics over many weights and samples. For instance, the train and test losses are aggregates over many samples. These quantities are occasionally described by simple empirical laws relating one to another. Such laws have already played an important role in shaping both our understanding and practice of deep learning. This pattern has ample precedent in the quantitative sciences. Many important physical and chemical laws were first discovered as empirical regularities and only later understood in terms of deeper principles, including laws due to Kepler, Snell, Boyle, Hooke, Faraday, Ohm, Poiseuille, and Planck. Given how often scientific fields have developed in this way, it seems likely that deep learning will continue to yield empirical laws as its science matures. Here, we highlight a handful of examples and conclude with takeaways for theorists. Figure 3. The loss of large neural networks decays according to predictable neural scaling laws. These neural scaling laws take the form of power laws linear on log-log plots in compute, dataset size, and parameter count. Reproduced from Neural Scaling Laws. The single most important measurement of any machine learning system is its test loss. Given the complexity of large deep learning systems, one might expect the test loss to be a complex, unknowable function of the system's hyperparameters. This is not so. Studies of neural scaling laws demonstrate that, within an architectural family, the final loss follows a predictable power law function governed by only 3 scalar variables: compute, the amount of data, and the network size. These power laws are shown in Figure 3. Why does test loss decay as a power law in these variables, and what determines the scaling law exponent? We still do not know. While scaling laws are often attributed to structure in the data, with candidate explanations in terms of the dimensionality of the data manifold, feature superposition, and power laws latent in task structure. They may also depend on details of the architecture and optimizer. At present, no framework can robustly predict the observed exponents a priori from dataset and architectural properties across realistic settings. See Open Direction 7, though recent progress has begun to move in this direction. The fact that test loss is so predictable strongly suggests that a simple underlying explanation remains to be found. Weight dynamics at the edge of stability. Because every model is the result of a training process, we would like to understand the dynamics and trajectory of a model's weights during training. While there are simple cases where these dynamics are exactly solvable, see Section 2.1, this is usually well out of reach. The loss landscape dictates the network's dynamics, but a direct visualization of the loss, as is done in Lee et al., suggests an immensely complicated landscape that is unlikely to have lawful regularities. Nonetheless, some robust patterns in the coarse, aggregate properties of weight trajectories have been found. One of these is the sharpness of the network loss surface, defined as the largest eigenvalue of the Hessian with respect to the parameters. When a typical network is trained using full-batch gradient descent with learning rate, eta, the sharpness undergoes two distinct phases: a gradual increase, termed progressive sharpening, followed by a plateau near 2/eta, Cohen et al., see Figure 4, called the edge of stability. Having identified these regularities, we can begin to understand them. Progressive sharpening provably occurs in deep linear networks, yet a quantitative explanation suitable to realistic nonlinear networks remains to be found. See Open Direction 8. More is understood about why the sharpness stabilizes at 2/eta. Particularly, 2/eta is the maximum stable sharpness achieved in convex optimization. Any sharpness larger than 2/eta would cause parameter oscillations of increasing magnitude. In more general cases, Damian et al. showed. Figure 4. Gradient descent occurs near the edge of stability. Three architectures are trained with full-batch gradient descent on CIFAR, 10 with varying learning rate, eta. Plots show the train loss, top row, and Hessian sharpness, bottom row. For each step size, eta, observe that the sharpness rises to 2/eta, dashed horizontal lines, and hovers at or just above this value. Reproduced from Cohen et al. How coarse properties of the third-order loss curvature can cause the second-order sharpness to stabilize at 2/eta. Follow-up work reveals that loss dynamics at the edge of stability can be decomposed as smooth, time-averaged, gradient flow dynamics plus oscillations in unstable directions. These works make quantitative predictions about the parameter trajectory, which closely match experiment. Coarse properties of hidden representations and weights. There are a handful of other cases in which coarse properties of neural networks' hidden representations and weights are known to obey simple equations. We will briefly mention three of these. Neural collapse. Consider a neural network classifier trained to choose among C classes. Papien et al. found that, at the end of training, the final hidden layer representations of samples from each class tend to cluster tightly around their class mean. Furthermore, the C class mean vectors form a regular simplex. Later theoretical work has explained this geometric arrangement as the natural energy minimizing configuration when A, the loss used is cross-entropy, and B, a small amount of weight decay is applied to the power 5. The neural feature ansatz. At the other end of the network, there are some robust regularities known about the first layer weights. Radhakrishnan et al. show that, after training, the gram matrix of the first layer weights, W subscript 1 to the power down act W subscript 1, aligns with the average gradient outer product. The product of a matrix and its transpose is proportional to the expected value of the outer product of the gradient of a function, where nabla subscript xf, x, theta, denotes the Jacobian of the network with respect to x. While this rule is heuristic and inexact, it often makes strikingly accurate predictions for quantities like the top eigenvectors of W subscript 1 to the power down act W subscript 1. Similar heuristics hold at deeper layers. At time of writing, there are only partial theoretical explanations for this phenomenon. See Zine et al., Boik-Satsura et al. Gradient flow conservation laws. A striking regularity identified in linear networks is that the difference between the covariance and Gram matrices of consecutive layers W subscript to the power down ac minus W subscript plus 1 to the power down ac W subscript plus 1 is conserved under gradient flow. What initially appeared to be a curiosity of linear networks was later shown to follow from continuous symmetries of the parameterization, an instance of the Noether principle, and thus could be used to identify similar conserved quantities in nonlinear networks. For instance, the risk-scaling symmetries in networks with homogeneous nonlinearities, e.g., real U, the scale symmetries preceding normalization layers, e.g., batch normalization, the translation symmetries in the logits preceding a softmax, and the rotation symmetries between key and query matrices in attention all lead to symmetry-specific statistics of the parameters that are conserved under gradient flow and weakly broken by SGD in predictable ways. Takeaways for theorists. Theory can be built bottom-up, starting from first principles math as in sections 2.1 and 2.2, or top-down, starting from empirical observations and attempting to explain them. In this section, we have highlighted a few notable examples of top-down theories. We expect more to come. The measurability of deep learning makes observation and empiricism a particularly fruitful approach, since experimentation can be iterated on quickly, while revealing mathematically simple relations and structure in trained models. Of course, some caution is necessary. Most macroscopic statistics don't obey a simple and general mathematical law, or at least don't seem to until plotted against the right quantity, and so the challenge is to find those that do. We encourage theorists of deep learning to proactively use experiments to look for lawful regularities in neural networks. 2.4 hyperparameters can be disentangled and understood. Training a deep learning system involves many numerical knobs, termed hyperparameters. These include optimization hyperparameters, such as the learning rate, batch size, momentum, and initialization variance, as well as architecture hyperparameters such as width and depth. The large number of hyperparameters in deep learning presents a challenge not only for practitioners, who must tune them carefully in order to achieve optimal performance, but also for researchers, who must grapple with many confounding factors when trying to interpret the outcome of scientific experiments. It is only in the last few years that the theory community has come to realize that hyperparameters can be disentangled and understood, and that the resulting mathematics is often both useful for practitioners and clarifying for theorists. This study of hyperparameters bears similarities to the study of the constant parameters governing the behavior of a physical dynamical system. For example, in a fluid flowing through a pipe, a dimensionless number called the Reynolds number computed from the pipe diameter and the fluid speed, density, and viscosity determines whether flow is laminar or turbulent. While solving for the trajectory of the turbulent fluid is extremely difficult, it is nonetheless very helpful to be able to quickly predict whether flow will be turbulent at all, and how things change if you scale up the pipe diameter or increase the fluid flow. Similarly, while solving the optimization dynamics of a neural network is very difficult, it is often very helpful to quickly obtain a coarse picture of how things change if you change one or more hyperparameters. In this section, we highlight two lines of work in which hyperparameters have been found to admit explanatory theory. Understanding optimization hyperparameters. Stochastic gradient descent has two hyperparameters, learning rate and batch size. The algorithm's dynamics are often invariant under a simultaneous rescaling of both. That is, if one doubles both the learning rate and batch size and halves the number of optimizer steps, or, equivalently, keeps fixed the number of training examples processed, then the trajectory stays nearly the same. This so-called linear scaling rule is useful for transferring a learning rate that was tuned for one batch size to a different one. A line of theoretical work has clarified this rule of thumb by interpreting SGED as a discretization of an underlying stochastic differential equation, SD, a perspective that predicts the linear scaling rule. Mant et al. Jastrzeebski et al. Chaudhary and Sawato. Lee et al. Maladi et al. Extended this line of work from SGD to adaptive optimizers, for which they argued that the learning rate should scale with the square root of the batch size. This invariance perspective explains how to adjust hyperparameters across batch sizes, but not how to choose the batch size itself. That choice involves an inherent trade-off between two resources: serial time, the number of sequential training steps, and overall compute, the total amount of computation, often closely tied to cost. For a practitioner who cares only about serial time and not at all about cost, the optimal batch size is the full dataset. Conversely, for a practitioner who cares only about cost and not at all about serial time, the optimal batch size is 1. In reality, no practitioner falls exactly in either bucket. A practitioner might care more about one resource than the other, but is generally willing to accept some slack in return for a better deal on the second resource. A frequently discussed concept is that of the critical batch size, a batch size which trades off between these two concerns. McCandlish et al. Proposed a simple model of this trade-off under which the Pareto frontier between serial time and compute takes the form of a hyperbola. Optimization hyperparameters in deep learning affect not just the speed and cost of training, but also the trajectory that training follows. This in turn affects various properties of the learned network, including generalization performance. Fruitful line of work has sought to explain these effects through the hypothesis that many implicit effects of optimizer hyperparameters can be understood as implicit regularization of loss function curvature to the power 6. Empirical studies initially observed that first-order optimizers regularize the curvature, i.e. Hessian, of the loss function, with larger learning rates and smaller batch sizes yielding stronger regularization strengths. Meanwhile, theoretical works in simplified settings showed that this effect can be explained by Taylor expanding the objective to third order, as such a calculation reveals that oscillating or fluctuating dynamics automatically induce curvature regularization. Building on this body of work, Cohen et al. Recently showed that for several optimizers in the full batch setting, the whole training trajectory on realistic neural nets is well modeled by a curvature-penalized gradient flow, where the role of the hyperparameters is to modulate both the form and strength of the curvature penalty. As a result, we now have a mathematical understanding of the learning rate in full batch gradient descent and are mostly free to instead study the simpler dynamics of gradient flow plus a loss curvature penalty. To the power 7, other analyses have developed analogous characterizations for stochastic dynamics in more specialized settings, Pezim et al. Chen et al. Fully extending this characterization to stochastic and adaptive optimizers would give us a common language for reasoning about the implicit effects of optimization hyperparameters on the training trajectory. It then remains to understand how these modifications to the training trajectory influence properties of the learned network. See Open Direction 8. Figure 5. The theory of network parameterization permits learning rate transfer across widths. Transformers of varying widths trained on Wikitext, 2 under standard parameterization, left, and μ-p right. Under standard parameterization, the optimal learning rate decreases as model width increases. Under μ-p, by contrast, the optimal learning rate remains nearly constant across widths, making it possible to predict the learning rate for wide networks from experiments on narrower, cheaper models. Reproduced from Yang et al. Disentangling architecture hyperparameters from optimization hyperparameters. There has been a highly successful line of work aimed at disentangling architecture hyperparameters such as width, depth, and output multiplier. See the lazy/rich dichotomy in section 2.2. From optimization hyperparameters such as the learning rate and initialization variance. The tensor programs framework makes this separation explicit, writing hyperparameters such as the learning rate in the form eta equals eta subscript 0, width to the power c, separating a scale-independent coefficient, eta subscript 0, from a width-dependent factor with exponent c. This line of work then asks, how can we set these exponents such that we retain interesting training behavior at infinite width? A remarkable insight from this analysis is that all non-trivial and non-explosive scalings give one of two limiting behaviors, analogous to the rich/lazy dichotomy in section 2.2 in the neural tangent parameterization (NTP). Features are frozen during. Figure 6. Universality across architectures and data modalities. Add different diffusion model architectures, from top to bottom, DDPM, a consistency model both based on UNet and UViT, converge to the same learned distribution and produce identical images when given the same input seed. Adapted from Zheng et al. As language models' performance, horizontal axis, increases, their internal representations become increasingly similar to that of vision models, and more so for larger models, from yellow to purple lines. Adapted from He et al. Training and in the maximal update parameterization, MUP, features evolve. Since feature learning is essential for most tasks, this analysis tells us that MUP is the scaling to use, resolving how hyperparameters should scale with model width. This understanding enables hyperparameter transfer. We can tune hyperparameters on small proxy models and then transfer them to large, production-size models, where they remain near optimal when both models are sufficiently wide. Figure 5. At the same time, the theory underpinning this result is asymptotic and does not fully account for its empirical effectiveness. In practice, models are trained at widths far smaller than the dataset size, and the usefulness of transfer depends on how quickly optimal hyperparameters stabilize with width. Nosai et al. And Ghosh et al. And Haya take steps toward closing this gap, providing evidence that a small set of spectral statistics stabilizes rapidly across widths under μp and approximately governs the optimal hyperparameters. This scaling-centric approach to hyperparameters was later extended to depth scaling, and leveraging this approach with other scaling dimensions remains an important future direction. See Open Direction 6. 2.5 Universal phenomena appear across settings and tasks. Deep learning is not a single recipe followed exactly every time. Different systems use very different architectures, datasets, training algorithms, and objectives, with ingredients combined in creative ways. This versatility has enabled successes on many tasks and modalities, including vision, language, speech, time series, protein sequences, and games. But the resulting model diversity makes it less clear how to approach the development of scientific theory. Do these diverse settings share deep commonalities we might hope to capture scientifically? Here, we review a growing body of evidence that there are indeed universal phenomena at play in these diverse settings. This is good news for theory. When many different complex systems exhibit the same universal behavior, it suggests that a simple underlying explanation may exist. We highlight this universality through three different viewpoints. 1. Different architectures reach comparably good performance on many tasks. 2. Different datasets share similar statistical properties. And 3. The learned representations and weights across different architectures and datasets are surprisingly alike. This roughly echoes examples of universality in which disparate physical systems share deep commonalities or display similar behavior at large scales, to the power 8. We end by highlighting a few theoretical successes in modeling universal phenomena. Universal inductive biases. Performance on a given task is often robust to variations in architectures, training algorithms, and objectives, in the sense that many alternate choices still lead to models that can solve the task. A well-known example is the choice between convolutional networks and transformers in computer vision tasks, which after much debate have been shown to obtain similar performance when matching compute, data size, and training recipes. In diffusion models, this similarity has been further shown to hold at the level of input-output mappings, with transformers and UNets generating near-identical images when fed with the same noise samples. As shown in Figure 6, these results strongly indicate that different architectures share similar inductive biases, despite their apparent differences. As a partial explanation, recent work has shown that assuming inductive biases towards locality and adaptivity to geometric structures leads to accurate quantitative predictions about the behavior of diffusion generative models. Universal structure in data. The no-free-lunch theorem states that generalization on completely arbitrary data with a common learning strategy is not possible. Therefore, deep learning must rely on particular features of the data present across all datasets and modalities on which it succeeds. For instance, many classes of images and audio signals share power law spectral properties, sparsity patterns, and multiscale structures, and can be analyzed with general-purpose wavelet bases. A similar phenomenon in text data is the ubiquity of Zipf's law. Word frequencies obey a power law distribution that holds over many natural and artificial languages. Hierarchical, compositional structure is also routinely used to model both images and text, which can sometimes be related through a common model. These shared statistical properties are a partial explanation for the ability of a single learning algorithm, say, a transformer trained with SGED, to tackle seemingly unrelated datasets, leaving only the finer-grained differences between them to be learned. Universality in representations. Going deeper in the internals of the network, it has been observed that representations learned by different networks can be similar across random initializations, widths, and architecture. It has been shown that networks trained to solve different tasks learn similar representations across training datasets, ImageNet and Places, 365, Link and Vidaldi, objectives, supervised or self-supervised, and modalities, vision or language. Furthermore, this similarity grows as model size and performance increase, hinting that neural activations converge towards a universal, Platonic representation, as shown in Figure 6. In simplified settings such as random feature representations, this convergence is a consequence of the law of large numbers applied to the feature kernels. In deep linear networks, it can be proven to arise from the implicit regularization of SGED. In more diverse settings, recent evidence suggests that the universality of representations may ultimately trace its origins to universal structure in data. Recent advances in identifiability theory also have shown that representational convergence happens at the global optimum of unsupervised, self-supervised, and supervised, Reisinger et al. Objective functions under a suitable data generating process. Several works have also shown empirically that this similarity can extend to the level of individual neurons, Li et al., Dravid et al., Kozla et al. In some cases, similar representations have been found in both artificial neural networks and biological neural networks, though the extent of this correspondence remains controversial. While a global trend towards similarity is emerging, it should be noted that the range of settings in which this convergence is observed, and its extent, are not fully known. See Open Direction 10. In particular, recent work has shown that this apparent convergence to universal representations depends crucially on the chosen comparison metric across similarities, Groger et al. A growing literature is devoted to understanding which representation similarity metrics one should choose in different circumstances, and highlighting the cases where they can be unified. If the mechanisms learned by large models are indeed universal, this is very encouraging for theory. Behavior shared across many systems should depend primarily on the features common to all such systems, and thus admit a description simpler than any particular model in isolation. Moreover, if the internal structure of trained neural networks primarily reflects the structure of data, then in studying neural networks, we may ultimately be studying the structure of data and its generating processes. See Open Direction 2. In particular, since language data comes directly from humans, understanding its structure may teach us something new and fundamental about ourselves. 3. Relation to other perspectives. There are several ongoing approaches to developing explanatory scientific theory of deep learning, each adopting a different perspective and using different sets of tools. We believe that these perspectives are essentially all complementary, all either directly seek a mechanics of learning or would symbiotically benefit from one. The statistical perspective. The rich tradition of classical learning theory remains influential today. To the Power 9, Bartlett et al. Offer a lucid summary of its central framing. Any statistical prediction method must balance expressivity to represent the richness of real data, complexity control, to make the most of finite training data, and computational efficiency, to yield practical algorithms. It is apparent that deep learning is sufficiently expressive, but it is not clear how a good function is selected from this enormous function class, nor why simple gradient methods suffice to train such complex beasts. The modern statistical viewpoint suggests two answers. Deep learning has an implicit inductive bias towards simple, well-generalizing functions, and despite their non-convexity, the very high dimensionality, over-parameterization, of neural networks makes optimization easy. These questions are good ones, and we believe these answers are basically correct. The challenge is now to make them precise in the case of neural networks. It is clear that doing so will require taking a close look at the nature of the training process. Only once we have done so will we be able to back out how this implicit bias arises and why gradient methods suffice for optimization. We do not believe these answers will be generic statements, but instead critically rely on important properties of deep learning and of natural data. The statistical perspective thus leads naturally to a serious scientific study of the mechanics of training. The information theoretic perspective. A closely related approach seeks to explain deep learning in terms of information theoretic ideas. In this view, learning is a process of extracting information from datasets, and a learning system works when it extracts information useful for prediction while discarding irrelevant information. This perspective hopes to understand learning as compression of the dataset into either the model's parameters or its hidden representations, with good generalization resulting when this compression is successful. Schwartz-Ziv and Tishby, Su and Rajansky. We find this perspective insightful, and it seems likely to us that a picture of this nature will hold. As with the statistical perspective, a major remaining question is how to make this view concrete and actionable. How do the architecture and training process of deep learning interact to actually implement this compression? And what factors make it more or less successful? Doing this, too, will require taking a close look at the nature of the training process, the architecture, the data, and their interactions. The information theoretic perspective thus also leads naturally to a serious scientific study of the mechanics of training. Physics of deep learning. This community descends from the older physics of machine learning lineage Hupfield, Amit et al., Gardner, and essentially seeks satisfying average case theories of neural network learning. To the power 10, the close relationship between physics and machine learning was recognized by the Nobel Prize in Physics. This approach is in line with, and has largely shaped, the perspective presented in this paper. And the project of this community is arguably the development of a mechanics of learning. The challenge then is to clarify important problems and coordinate effort for efficient progress. Perspectives from neuroscience. Several approaches to developing a science of the brain suggest approaches to developing a science of deep learning. One approach starts from hypotheses about neural systems, for example, that their computation amounts to some form of approximate probabilistic inference, and seeks to make deductions and predictions from this hypothesis. Some of these predictions seem to hold suspiciously well in deep learning. See, for example, the case of edge-selective cells in the visual cortex, Olshausen and Field, and edge-selective receptive fields in convolutional networks. Another approach, termed systems neuroscience, seeks to directly decompose subsets of the brain into interpretable circuits and reverse engineer the structure of their learned representations. This approach resembles mechanistic interpretability, which has adopted some of its methods and intuitions. We expect and encourage this dialogue to continue, and it seems plausible that some of these high-level hypotheses about the brain, e.g., that the brain admits at least a partial decomposition into interpretable circuits and that local circuits implicitly solve inference tasks, will turn out to be true of deep learning. The reasons these facts are true, if indeed they are, is surely bound up in the dynamical way learning actually happens. A study of the mechanics of learning is thus important to the continued exploration of these ideas. Developmental interpretability/singular learning theory. This approach, which grew out of the mechanistic interpretability community, seeks first principles predictive theories of neural network learning based on the singular learning theory framework of Watanabe, emphasizing a Bayesian perspective and aiming to understand training as a process of sequential phase transitions mediated by the geometry of the loss landscape. Hoogland et al. We see this community as seeking the same goal we suggest here, a fundamental mechanics of learning, and a rigorous foundation for interpretability, but with a toolkit that differs from the other listed perspectives. There is potential for fruitful cross-pollination and tool sharing between these different approaches. Science of deep learning. It has long been appreciated by practitioners that machine learning is largely a practice of trial and error, and that it may be possible and beneficial to systematize it. Indeed, much of the rapid empirical progress of the last decade resulted from systematic organization around agreed-upon benchmark tasks. Nonetheless, the training and application of large models remains more alchemy than science. We believe that a fundamental mechanics of the learning process is the foundation on which this science will finally be built. 3.1 Learning Mechanics Mechanistic Interpretability. We discuss mechanistic interpretability specially because there is a unique opportunity for cooperation. Mechanistic interpretability aims to understand trained neural networks by identifying the internal mechanisms, features, circuits, and learned algorithms that give rise to their behavior. At its core, this approach is guided by the belief that neural networks admit a human-understandable, mechanistic description that can be uncovered through careful empirical reverse engineering to the power 11. This approach has already borne fruit. Many visually striking or interpretable mechanisms have been discovered in large models to date, to the power 12. This is a complementary perspective to our own and presents a wonderful opportunity for symbiosis. At time of writing, mechanistic interpretability remains largely a qualitative science, more reliant on human-judged empirics than on compact mathematical principles or simple governing laws. This is quite natural. Semantically meaningful functions resist mathematical characterization, to the power 13. On the other hand, a mechanics of learning would be quantitative by definition, but by the same token will be too low-level to answer important questions of semantic meaning on its own. These approaches study the same system, i.e., deep learning, at different levels of abstraction, and so of course they can and should work together for mutual gain. Calls for rigorous foundations for interpretability have been steadily growing, and this is one thing learning mechanics can and should seek to help provide. In turn, mechanistic interpretability offers learning mechanics a rich and growing tableau of empirical phenomena ripe for the development of explanatory mathematical theory. Learning mechanics mechanistic interpretability. We emphasize two complementary avenues through which learning mechanics can support mechanistic interpretability, formalizing core assumptions and explaining how mechanisms develop through training. Formalizing core assumptions. Learning mechanics can make explicit, formalize, and, where necessary, challenge the core and often implicit assumptions that guide interpretability research. These include linear representability, that features correspond to meaningful directions in activation space, Nikolov et al., Park et al., Nanda et al., Marx and Tegmark, Jiang et al., Sordas et al. Locality, features and circuits are localizable to particular subsets of model components, Meng et al., Wang et al., Kami et al., Aurora et al. Sparsity, that individual features and circuits are activated or functionally relevant on only a small fraction of inputs, and compositionality, that complex network representations and computations arise from the composition of simpler, modular submechanisms. These core assumptions underpin the identification, isolation, and analysis of the internal mechanisms of trained neural networks in mechanistic interpretability research. A mathematical theory of learning offers a way to clarify the regimes in which these assumptions hold, the conditions under which they fail, and the sense in which they can be derived from training dynamics and data statistics. See Open Direction 4. Explaining how mechanisms develop through training. Mechanistic interpretability has generally prioritized describing what mechanisms trained neural networks have learned, and there remains a rich opportunity for work which aims to explain how and why such mechanisms form in the first place. There is already substantial interest within parts of the interpretability community in this dynamical/theoretical perspective, including work on the formation of induction heads, grokking, and progress measures, sudden phase transitions in circuit formation, and the research program of developmental interpretability, discussed earlier. Our goal is not to replace these efforts, but to encourage deeper engagement between mechanistic interpretability and the broader landscape of mathematically grounded ideas and tools in learning mechanics. Echoing Safra. We hope that learning mechanics can play a role analogous to evolution in biology, just as nothing in biology makes sense except in the light of evolution. The internal mechanisms of trained networks may be most naturally understood in the light of the processes that give rise to them. Learning mechanics' mechanistic interpretability. Conversely, learning mechanics has been deeply influenced by the empirical discoveries of mechanistic interpretability, which often identify concrete phenomena that invite first principles explanation. Mechanistic interpretability places the structure of data at the center of its analyses, revealing settings in which the relationship between input structure and learned mechanisms is especially clear. By contrast, much of classical deep learning theory has relied on highly simplified data models, leaving a gap between theoretical predictions and behaviors observed in practice. In this way, mechanistic interpretability helps bridge this gap by providing learning mechanics with concrete, well-defined targets for theoretical modeling. Several such observations have already proven influential in stimulating work in learning mechanics, including the emergence of induction heads for in-context learning, the role of Fourier features in algebraic tasks, and the geometry of features arising from the structure of correlations in the data. Just as the development of physics was often driven by empirical discoveries in adjacent fields, we expect progress in learning mechanics to be driven by theorists who take seriously empirical phenomena, including those uncovered by the mechanistic interpretability community, and seek to explain them. For reasons for skepticism and responses. We have made a case that an ambitious mathematical theory of deep learning is possible and that developing this theory is a worthwhile endeavor. This is far from a universal view, and so we now address common counterarguments that a theory of deep learning is either not possible or not a goal worthy of our effort. Competent researchers have been trying to develop a theory of deep learning for decades, and we don't have one. Surely if there was a theory, we would have already found it. It is true that machine learning theory is a field with a long history, and certain avenues for developing theory have been thoroughly explored. Why should now be different? There are several reasons for optimism. First, the practical success of deep learning is comparatively recent, and we have a wealth of new empirical systems to study and mine for explainable phenomena. Some of these phenomena, like the apparent convergence to universal representations discussed in Section 2.5, were only revealed by the last few years of model scaling. These developments have turned the search for a theory of deep learning from a mathematics into an empirical science, and one with no lack of interesting things to measure. We now have much better means to ask questions and check our answers in a tight feedback loop. Second, the field is much bigger. Empirical successes have attracted researchers from physics, mathematics, neuroscience, and other adjacent fields, and so we have more and more diverse minds on the case. Third, it is worth noting that the development of major sciences has usually taken at least several decades, so we should not be too discouraged that we do not yet have all the answers. The objects currently understood from theory are very primitive compared to e.g. LLMs. Surely first principles understanding of large models is too heavy a lift. Indeed, we expect that building up to LLMs will be a heavy lift and take considerable time. The near-term hope is instead that some understanding of the basic building blocks of deep learning will prove useful even without a constructive theory that explains the whole model. We can see this happening already in isolated pockets, including empirical scaling laws, Section 2.3, mathematical prescriptions for hyperparameter scaling, Section 2.4, neural tangent kernel-based methods for data attribution, Park et al., and theoretically motivated optimizers. These local theories of small pieces of the deep learning stack are useful for hyperparameter scaling in large models, even though they are in no way comprehensive theories of the model. One might hope for similarly useful local theories that treat subjects like training instabilities, dataset selection and attribution, or the effect of normalization layers. It is also important to stress that the identification of the right basic objects in a field of science often makes it possible to ask applied questions in a more sensible way. Consider, for example, how the understanding that all matter is made of atoms underlies virtually all other basic science, and how knowledge of electromagnetism permits optical and radiological tools in countless applied disciplines. As discussed in Section 3.1, we hope that learning mechanics can offer tools that adjacent fields such as mechanistic interpretability can apply to better carry out their work. In this way, rigorous work on primitive objects can aid the applied science of large models even without a rigorous theory that builds all the way up. What matters is a model's high-level behavior. Microscopic theories are too zoomed in to see this. Models' high-level behavior is indeed important. How does this fit in with the lower-level sciences of deep learning? We argue that deep learning may be studied at the level of physics, biology, or psychology, with this last including the study of the model's capabilities, personality, and goals. It seems likely that study at all levels will be necessary. Learning mechanics, the physics of deep learning, is the farthest from model psychology, with mechanistic interpretability, the biology, lying in the middle and connecting the two to the power 14. We don't need a theory of deep learning, we need a theory of data. We think we need both. We need a theory of the structure in data and a theory of how a parameterized model learns it. We touch on the necessity of developing a useful theory of data in Section 2.5 and Open Direction 2. These are both part of the project of developing a mechanics of learning. AI will understand itself before we do. Why try to build theory? This is a present concern for human intellectual endeavors across the board. Our response here has three parts. First, theory is already useful and will continue to be more impactful as it develops, so this scientific work is likely to make a near-term impact. Second, it seems unlikely that AI working in isolation will suddenly and separately solve deep learning theory. It seems more likely that breakthrough progress in a transitory period will come from human scientists using or working with AI, and expert humans will remain in the loop. Third, if one's goal is AI safety, some human oversight of AI systems will be necessary, unless one trusts the AIs to fully police themselves, and having a human parsable theory of deep learning gives us a foot in the door. 5 Open directions in learning mechanics. It is important for any field, at any stage of development, to have a sense of its important open questions and goals. In this section, we present a curated list of open directions which we expect can be solved by a theory of the mechanics of learning in the next decade. These directions are loosely ordered by their connection to the lines of evidence introduced in Section 2. We hope this helps sharpen a shared research agenda. For a longer catalog and a forum for community discussion, see learningmechanics.pub/openquestions. Open Direction 1. What are simple, solvable models of genuinely deep, nonlinear learning? As discussed in Section 2.1, deep linear networks and kernel methods are the two main workhorse solvable models of learning mechanics. The first captures nonlinear dynamics of the parameters, and the second learns nonlinear functions of the data. While a few special cases of solvable models with both forms of nonlinearity are known, no unified framework has emerged. Can we get the best of both worlds while maintaining some level of generality? Is there a class of solvable model that captures both deep, nonlinear dynamics and nonlinear function learning? Can such models illuminate new things about feature learning, the role of depth, optimization phenomena, e.g. progressive sharpening, and architectural innovations, e.g. normalization layers, residual streams, self-attention, and gated nonlinearities? Can it be usefully applied to modern learning paradigms like self-supervised learning, reinforcement learning, and denoising diffusion? Open Direction 2. What would a theory capable of capturing natural data look like? Deep neural networks find and exploit structure in natural data. This means that the structure of the data must somehow enter into our theories. What is this structure and how do we find it? Despite the complexity of data, in many cases models appear to derive their learning signal from a small set of sufficient statistics. What are these minimal data statistics, and how do they enter into a predictive theory of what the model learns? Are these statistics different for different models and at different stages of training? Can we describe the relevant structure in a dataset in terms of a model with free parameters found via an empirical fit? Open Direction 3. Does deep learning implicitly minimize some notion of functional complexity? Deep networks trained by conventional optimizers are widely believed to have some sort of bias towards learning simple functions. This idea has surfaced many times under different names, e.g., implicit regularization, maximum margin bias, simplicity bias, and spectral bias, but has only been characterized precisely in highly specific settings, and a general picture has not been found. Do deep neural networks broadly seek to minimize some precise notion of complexity among functions with low loss? If so, what is the appropriate notion of complexity? Kolmogorov, circuit, weight norm, or something else? In what settings or limits is this minimization exact, and when is it only approximate? Do the sparse features and circuitry studied by mechanistic interpretability naturally emerge as the solution to this minimization problem? Open Direction 4. How do we formally define the features learned by neural networks? Mechanistic interpretability seeks to identify and disentangle the features, circuits, and mechanisms learned by neural networks. Can these concepts be given precise mathematical definitions grounded in first principles? What formal structures naturally emerge from such a definition? Can we use these notions to evaluate and formalize central assumptions of mechanistic interpretability, including linear representability, locality, sparsity, and compositionality, as discussed in Section 3? How do these ideas connect with the less semantically meaningful, but more precise, rich versus lazy picture of feature learning discussed in Section 2.2? To the power infinity, Open Direction 5, are finite neural networks properly understood as approximations to infinite limits? In Section 2.2, we articulated the discretization hypothesis, which states that finite neural networks are simply discretized approximations to infinite networks, analogous to how a spatiotemporal discretization is used to numerically approximate the solution to a differential equation. For network width, the limiting continuous object is the measure of neuron activity in hidden layers, while finite depth in a residual network can be viewed as a discretization of a neural SD or OD. Small step sizes can render stochastic optimization algorithms approximately equivalent to some kind of flow. In this view, increasing model size and decreasing learning rate while commensurately increasing step count serve essentially to improve model performance by decreasing discretization error at the price of additional computation. Is this the right way to understand width, depth, learning rate, and other finite hyperparameters in deep learning? What does the limiting continuum system look like? Open Direction 6. Can we understand and eliminate all hyperparameters? In Sections 2.2 and 2.4, we outlined a research program in which hyperparameters are systematically analyzed, disentangled, and in some cases removed by taking appropriate limits. How far can this program go? Can we reach zero hyperparameters, or are some hyperparameters irreducible? If we eliminate all hyperparameters, what remains? Open Direction 7. Can we predict scaling law exponents a priori? As discussed in Section 2.3, large models exhibit robust power law scaling of loss with respect to model size, data, and compute. The observed exponents are non-trivial. They do not appear to be simple fractions which might result from elementary dimensionality arguments. It is widely believed that these values are driven largely by structure latent in the dataset, but may also depend on details of the architecture and optimizer. While many explanations for scaling laws have been proposed, a decisive test of any such theory is its ability to predict these exponents quantitatively from first principles. At present, no framework can robustly do so across realistic settings. Can we develop a theory of scaling laws that both explains why power laws arise and predicts their exponents a priori? What measurements of the dataset, architecture, and optimization are required to do so? Open Direction 8. How does loss curvature interplay with architecture, features, and generalization? As discussed in Sections 2.3 and 2.4, a significant feature of deep learning optimization is that the optimizer implicitly regularizes the curvature, i.e. Hessian, along its trajectory. by steering towards regions of the lost landscape with lower curvature. While progress has been made on formalizing this effect using curvature-penalized gradient flows, it remains unclear how these curvature dynamics relate to other concerns in deep learning theory. Why does the curvature tend to rise in the absence of any such implicit regularization, and can this progressive sharpening be attributed to certain properties of the architecture or data distribution? How does the implicit curvature regularization affect the features that are learned? Why does it sometimes lead to improved generalization? Hashtag OpenDirection9. What makes for a good optimizer in deep learning? It remains fundamentally unclear why some deep learning optimizers work better than others. Why do adaptive methods such as ADAM and Muon consistently outperform simpler alternatives like SGD when training large language models? How does adaptive preconditioning in these optimizers interact with a network's architecture and loss landscape to lead to faster, more stable training? Can we identify fundamental principles that explain the success of modern optimizers, predict when they will fail, and guide the design of new ones? OpenDirection10. In what sense do large models trained differently learn similar representations? In Section 2.5, we discussed evidence that large models trained from different random seeds, and sometimes even with different widths, architectures, data, or objectives, tend to learn similar internal representations. A precise version of this claim would be very powerful. Understanding how representation learning is universal would give us confidence that theory developed for one model and setting transfers to many others. The central difficulty here is methodological. How do we assess similarity? There is no single way to compare high-dimensional representations. Metrics based on kernel alignment, nearest neighbors, model stitching, and more compare different aspects of representation geometry. Which ones are stable across training regimes? What is the appropriate metric that quantifies this similarity? What is the largest range of experimental settings under which convergence is observed? What are the representation universality classes? 6. How to get involved in the development of learning mechanics. It is always difficult to start doing research in a new field. Consequently, we would like to make it as easy as possible for newcomers to get started. In this section, we extend a hand with some encouragement and advice. There is no specific academic background required to do useful work in this field. Well-regarded researchers in deep learning theory come from backgrounds in physics, mathematics, computer science, neuroscience, statistics, and more. Moreover, knowing another field well is useful, and established ideas from other fields can be applied to deep learning in some form or another, as the diversity of perspectives on deep learning theory attests. Section 3. Good things grow from cross-pollination. A firm grasp of undergraduate mathematics, a familiarity with deep learning, and a desire to learn are the only definite prerequisites. 6.1 Tenets for getting started. If you want to join this field, you are more than welcome. While there is no single correct way to craft theory, there are plenty of pitfalls that many of us encountered when starting out. To help avoid some of them, we have compiled a short list of guiding principles for doing research in this field. These tenets are not intended to maximize your number of citations in the short term, and following them may involve some swimming against the current of academia. Instead, they are intended to maximize your impact in the long term and your ability to integrate and contribute to the community. Do experiments frequently. As discussed in Section 2.3, deep learning is a field where the cost of doing experiments is relatively low, with a fast turnaround time. Use that to your advantage. Experiments serve to check assumptions, inform theoretical models, reveal the limitations of a theory, peer beyond the cases that a theory covers, and surface interesting phenomena to study in the first place. Try to include experiments in every paper and make them as simple and revealing as possible. Simplicity and insight matter more than technical complexity. If you want to do work that is useful for others, they need to understand it, not merely be impressed by it. Take the time to simplify your findings, identify the underlying intuition, and check with simple experiments. A useful idea for thinking about a type of problem is generally more valuable than a difficult theorem or a solution to any particular problem, so emphasize these useful ideas when you present your work. This will make your results more accessible and easier for others to extend and apply. Your conference reviewers may disagree with this philosophy. The conference system tends to reward technical complexity and undervalue simplicity, but it will make your work more impactful in the long run. Value scientific understanding over state-of-the-art performance. Applied deep learning is a field of engineering whose progress is measured by benchmarks. For scientists of deep learning, the game is different. Your contribution is gauged by your contribution to collective understanding. It is easy to feel pressure to tack on some engineering benefit in a scientific paper to make the paper seem more relevant and timely, but doing so usually dilutes the paper's scientific contribution without really affecting practice. Of course, fundamental science should eventually improve state-of-the-art performance, and when this naturally falls out of the science, it is a powerful way to demonstrate what has been understood, to the power 15. When it does not, though, there is no need to force it. Set benchmarks aside for the time being and seek understanding on its own terms. Don't try to do it alone. Deep learning is a field with a lot of history and many known results, and guidance from a live human will help you. You can get pretty far from reading material online and talking to AI, but it doesn't replace human collaboration and mentorship. You should seek out other people interested in this area, ask for their feedback, and ask to work with them. A weak corollary to this is, when one exists, watch the talk version of a paper in addition to reading it. A great deal more of the nuance of a project is conveyed through in a live presentation. The Physics Meets ML and Physics of Learning series are good places to look for talks on what we here call learning mechanics. 5. Try a few different problems before going deep into one. Deep learning theory has so many open questions that you probably won't know where to start. That's okay. Just jump in and feel free to change problems a few times early on to the power 16. Knowing multiple areas is essential to having high-level ideas anyways, and working in an area is the best way to learn it. 6. Invest in fundamental tools and techniques. Compared to more established fields of science, mathematics, and engineering, deep learning is very young. These other fields have identified deep ideas and developed powerful tools applicable to broad classes of problem. Learning these fundamental tools comes in handy when similar problems arise in deep learning. For example, statistical physics and random matrix theory have powerful tools for thinking about high-dimensional interacting systems, and these tools are of great use in learning mechanics when one takes infinite limits. Many of the central ideas of classical optimization theory make regular appearances in the study of neural network optimization. Other concepts from statistical signal processing, such as wavelet decompositions, graphical models, and information theory, have been comparatively less leveraged so far, but may prove to be useful and complementary tools of learning mechanics. We will put as much useful introductory material as we can on learningmechanics.pub, and we encourage discussion in the comments there. We also encourage taking a crack at the open directions in Section 5. Work hard, have fun, and best of luck. We hope to see a great deal more fundamental science of deep learning in the next few years. Acknowledgements. We are grateful for feedback on this paper from many people from several overlapping groups. Researchers working on the theory of machine learning, researchers working on AI safety and mechanistic interpretability, practitioners and applied deep learning scientists, neuroscientists, and physicists. This includes Alberto Bayetti, Alex Infanger, Alex Williams, Emil Dravid, Anthony Thomas, Avrajit Ghosh, Bin Yu, Bruno Loureiro, Chandan Singh, Clementine Domini, David Berman, David Clint, Denny Wu, Ev Gunter, Honam Wong, Itai Levy, Jacob Yates, Jacob Zavatone Veth, Jeff Gore, Jesse Hoogland, Jia Chao Fong, Jingfeng Wu, Caden Tro, Lauren Greenspan, Lenka Zdibarova, Lily Stelling, Lucas Bongartz, Nina Myelane, Noah Rubin, Peter Bartlett, Raymond Fan, Samyuk Jain, Sufyan Haya, Sultan Daniels, Wanyu Lei, Yasemin Bari, and Zohar Ringel.